In this section of the course on telecommunications, we want to talk about how basic telecom devices work. In order to do that, we have to understand elements of the field of electromagnetism. Every telecommunications device is an electric device, and in order to understand electricity, we also have to understand magnetism because they are correlated. Every time you have electricity, you also have a magnetic field around that electrical current, and likewise you can take a magnetic field and exploit it to produce an electrical current as well. So electromagnetism is the intermixing of these two phenomena of electricity and magnetism. Here we show bar magnets with south and north poles. Everyone is familiar with magnets just from their experience of experimenting with these as a child. And these dotted lines here show magnetic lines of flux. Those are the force lines that are either attracting or repelling the two bar magnets. Now, when we look at the magnetic lines of flux, here we have north pole of one bar magnet near the south pole of another magnet. So these lines are lines of attraction. These two bar magnets are pulling themselves towards one another. And in fact, the closer they get to one another, the stronger that magnetic field. They want to cling together and join those two poles. Likewise, if we were to switch the situation around, we would have like poles repelling one another. And so that can be shown here in this next slide. Here we have a bar magnet, and the bar magnet alone has magnetic lines of flux between its north and south poles. In fact, we can take this bar magnet and shape it in the form of a U and have a horseshoe magnet and still have these magnetic lines of flux between the north and south poles. Here now we see two bar magnets with like poles repelling one another. That's because the direction of both of these magnetic fields are in the same direction, and so pushing one bar magnet towards the other makes the other one repel and push away from it. So like poles repel, opposite poles attract. If we flip one of those bar magnets around, the one on the right, now the north and south poles are attracting one another. We want to compare this with the properties of matter because matter has these magnetic properties as well. Here we're looking at an atom of copper, and that copper element is atomic number 29. So copper has 29 protons and neutrons in the nucleus and 29 electrons that orbit around the nucleus. All of the electrons are negatively charged, the protons are positively charged, and the neutrons are neutral. Also, we have electrons in shells. The innermost shell contains 2 electrons. The second shell contains 8 electrons for a total of 10 so far. And then the third shell contains 18 electrons. 2 plus 8 plus 18 is 28. There's one lone electron in the outer shell called the valence electron. The valence shell is the outermost shell, and that means that copper is very reactive. It will easily give up this lone electron in its valence shell, so that when we have a copper wire, what we have are a dense clustering of all of these copper atoms. What this means is this negatively charged electron can be easily coaxed to move when we apply a potential source, a source of potential energy, like a battery, to both ends of the copper wire, and we can actually get these electrons to move through the copper. That movement of electrons through the copper is basically electricity, and we'll want to describe this phenomenon and compare it to how the magnetism works with the bar magnets. Here we see a magnetic field that's induced by current in a simple electrical circuit. In this circuit, we have a battery over here, and a battery has a positive end. This battery's positive end would be at the bottom, and the negative end would be at the top. The way I can tell that is because the electrical current is going in this clockwise direction. Now remember, electrical current is the flow of electrons, and electrons are neutral, actually negative in nature. And so the negative end of the battery up here would repel the negative electron charge, just like similar poles of a magnet repel one another. So this negative source here repels electrons to go this way. And in this diagram, it's only two-dimensional, but imagine that this wire comes through the sheet of paper straight out at you. On this paper, if we put iron filings are going to react to the magnetic field. We'd see that the iron filings form concentric circles on this flat paper when the electrical current goes through the center wire. This demonstrates directly that an electrical current has an associated magnetic field around it, which is directional. In fact, that's what's shown in this diagram here. If this is our copper wire, and this is just a cross-sectional cutout of it, if the current is going in this direction from left to right, the magnetic lines of flux go around it in this direction. It's called the left-hand rule because if you take your left hand and put it along this wire, your thumb indicates the direction of the current, and your fingers would be curling around it going clockwise as the wire comes straight out at you. So if your thumb is pointing at you, your fingers are going in a clockwise direction. That's the direction of the magnetic field around that electrical current. Now, I want to compare electrical flow with water flow because water flowing from one vessel to another is much more intuitive. And so on the left here I have a full drum of water, and on the right we have this empty drum, and they're connected by a pipe. Now I have a valve here so that the water is currently turned off, so there's no flow of water in the pipe. But as soon as I open the valve, if I open it all the way, we'd get a flow from the left drum into the right drum. So this flow of water from left to right is like the flow of those electrons. It's like the current, the electrical current. Now, there's a resistance to this flow, and in this mechanical system, the resistance to the flow is basically the diameter of this pipe. The smaller the diameter, the higher the resistance, and the slower the vessel on the left empties into the vessel on the right. And that's like the electrical property of resistance. There's a resistance to that flow of water. Also, there's a potential energy here, and I place the left vessel higher than the vessel on the right, and that's because gravity is in effect, and so gravity is what makes the water flow from the left drum into the right drum. Well, this height of this column of water is potential energy. It's like a bowling ball sitting on the edge of a table. That also represents potential energy because if the bowling ball rolls off the edge, it crashes to the floor. Well, that potential is represented by that gravitational force that'll be released when the bowling ball rolls off the edge of the table. And the same thing is here when the valve is closed. There's a potential energy, and that electrical potential corresponds to something called voltage. So in this simple mechanical system, we have flow of water, which relates to flow of electrons, and that's current. We have resistance to the flow in the diameter of the pipe, and that's equivalent to electrical resistance in the conductive material itself, the copper or other material that might insulate it, insulating material. And then we have the potential energy, which is equivalent to voltage in the electrical circuit. So we look back at our simple DC circuit here. The DC is electrical direct current, and that's what a battery source is. It's a source of direct current. The potential difference is measured in volts, and so the potential between this positive terminal on the battery and the negative terminal is measured in volts, of voltage. And as the electrical current flows, those electrons move through the copper wire with the corresponding magnetic field given by the left-hand rule, and the electrons flow away from the negative source towards the positive source because of their magnetic-like property. Remember, electrons being those negatively charged particles that orbit in the outermost layers of the atoms.